I am Dr. Diane Gardner from Cardiff University. For the past few years, we've been looking at self-healing concrete. So this is concrete that has an ability to sense and respond to damage.
And why do we need this self-healing concrete?
Well, a lot of our infrastructure in the UK suffers from cracking, and therefore we have to spend inordinate amount of money on repair and maintaining our infrastructure. And therefore, if we're able to give concrete this ability to self-repair and self-heal, then we can save a lot of money in the process.
So what kind of areas are you looking into to give concrete this self-healing property?
So there are three main mechanisms that we're looking at. The first is being able to control the opening of these cracks by using fibres, and these fibres can take the form of plastics made from recycled plastic bottles, for example. The second mechanism is bacteria, so this is bacteria that can survive in concrete and then can be rejuvenated when cracks occur and eat the food really that we've placed in the concrete to help it out, and will produce a biological cement, so a natural limestone, as we would say in geological terms. And the last one is using capsules, whether they're nano or micro capsules, that contain healing agents like resins or glues, and we can place these inside of the concrete and they can rupture and release healing agents once damage occurs.
Okay, well, as a microbiologist myself, I find this idea of bacteria kind of lying dormant in the concrete waiting for it to get damaged fascinating. But how would you attempt to limit the regrowth potentials? I can just imagine these bacteria going out of control and producing all this aberrant concrete. Have you looked into this?
We haven't really looked into it, but I think the challenge isn't necessarily them going out of control. It's actually trying to promote their growth in the concrete, because concrete is such a highly alkaline environment for the bacteria. Then there are only a few strains which can really survive in that sort of scenario, in that sort of context. And therefore it's really getting them to grow and deposit this biological cement that's a challenge, rather than trying to limit them. And they're only ever going to be active when they have moisture, so water and oxygen, and that's only really ever going to happen in the instance of a crack occurring. So they're really not going to do anything until those cracks appear.
And could you elaborate a bit on the polymer, the recycled plastics, and where they'd come from and how you'd envisage them working in this repairing concrete?
Okay, so in the laboratory scale at the moment, we've tried tendons of this polymer material. So this is polymer that has a memory. So as strange as it sounds, it's got a shape memory. So these are polymers that have been drawn, they've been frozen in their state, and then what we do is we place them into concrete, and then upon activation, they can actually shrink, and when they shrink, they create a stress, a force within the concrete that actually helps to close these cracks. And the material that we can use them from, well, it's general plastics, but we're thinking that we can use these recycled bottles that will be collected from the weekly refuse collection as part of the process. But yeah, it's really the shape memory effect that we're relying on there to sort of close the cracks, to the ability that you can get concrete actually to heal what we call autogenically. So naturally, even without these other glues or resins or bacteria in there, we can actually rely on concrete alone to heal itself, as long as we can close the cracks sufficiently to allow that to happen.
And so you say these polymers would be activated. What's the activation mechanism there?
That's a challenging aspect, I think, because at the moment they've been activated in the laboratory by heat, so by temperature and perhaps steam. We really are looking into that at the moment in terms of various other mechanisms by which we can activate them. So maybe it might be running electrical wire down them, which heats them up, which shrinks them. But essentially at the moment they're heat activated, so there is some development there. I acknowledge that in terms of getting that to work in a larger scale.
And if these polymers are activated, closing the cracks, are they going to cause cracks elsewhere? If they're bringing together a fissure, will they create other fissures around the edge of that zone?
They shouldn't do, because the idea is to have significant numbers of these fibres that are dispersed within the concrete, such that when they're all activated, you get what we call in civil engineering, or what we call in engineering, a confinement. So you have a three-dimensional shrinkage in the concrete, and when you have that level of confinement, you actually get concrete which then becomes very, very ductile, so it behaves very, very differently to the brittle state that we know it.
And could you briefly tell me about this capsule, the nanocapsule technology?
So the nanocapsule technology, or the microcapsule technology, is being developed by our colleagues at Cambridge University, and they're looking at really adapting the form of the microcapsule such that it is more responsive to different stimuli. So perhaps it's of a certain material that will be quite ductile, quite supple when you actually cast it into the mix, but will then embrittle with time to make it rupture. Maybe it might be responsive to different changes in pH. Or if we look at the main reason why we're doing a lot of this is because we get corrosion. The cracks in the concrete actually relate to or have an influence on the corrosion of the reinforcement. And you get electrochemical reactions occurring, and therefore if we can make these capsules respond to electrochemical stimulus, then we start getting a system which is working together to heal these cracks. So really they're under development. They're working with their chemistry department at Cambridge University to further these capsules.
Diane, how far are we from seeing this in our local skyscraper or on the road? How close to application is this technology?
I think in the immediate future, so we're talking in the next 2 to 3 years, we'll have applications in non-critical situations. So we're working quite closely with a civil engineering contractor in developing and identifying scenarios in which we can use this material. And then really from then on, it's a case of widening out our prospects and talking to the industry as a whole to introduce them to this new material and to see if there's a way forward in which we can use it. So I'd say 3 years for a demonstration of it at real scale, and then forwards and onwards from there. So watch this space, I think.